We've introduced electricity generation, both in the context of vertically integrated monopolies and competitive wholesale electricity markets. Now we're going to talk about electricity generation from renewable sources. What are the types of renewable electricity generation? We have wind power, we have solar power, we have hydro from dams, geothermal. There's some of that in the United States, not a ton yet. And then we also have tidal. There's other sources that are small, but they do exist. But probably the top ones are the first three here, and then I'm just listing a couple of potential future ones below. Wind and solar are becoming a larger share of U.S. generation. So the little figure on the right here is from the Energy Information Administration. That's the government agency that tracks energy use in the United States. You can see the brown line is coal generation over time from 1950 through 2020. And the stuff on the bottom is renewable production. The bottom dark blue is hydro. Wood is in there somewhere, and waste energy production is in there. And then you have so wood is an interesting one because this is just energy to heat people's homes. We're not producing electricity from wood, so this is kind of not the most accurate figure for electricity production and consumption, but this is overall energy. Biofuels is also that's used in transportation, not electricity consumption. You can see geothermal is a tiny fraction here, and then wind and solar are the top, the green and the yellow. Now, wind has increased over time, so has solar. And this is showing that combined, the renewables are, in terms of energy production, total energy production, are meeting the total coal production. But if we take out the stuff for transportation, biofuels, and wood for heating homes, then we're still producing less renewables than we do, less electricity with renewables than we do coal. So electricity generation from wind and solar is still small relative to total generation. So now we're looking at just electricity. Natural gas is the largest share in the U.S., coal the second largest, nuclear the third, and then we have hydro and wind competing for the fourth largest, and a little bit of solar in here, and we have some renewables minus hydro, solar, and wind is the little yellow sliver in this pie chart. There are other sources like other gas and petroleum liquids, but these are incredibly small. What are the features of renewable technology? Renewables have high fixed costs and low marginal costs. They're still often more expensive than conventional generation, but renewable prices are falling, which we will see in a moment. High fixed costs meaning they cost a lot to build, but they're low in operating expenses. Basically, you don't have to buy fuel to run them. You don't have to buy coal and natural gas. So the marginal costs are extremely low. The fuel, essentially wind and sun, is free. This is in contrast to a coal plant or natural gas plant, which costs less to build per megawatt hour, but you have some marginal costs. And we'll see how to compare these in a moment. There's limited flexibility for choosing locations, and we'll talk about that. And generation is intermittent, which also causes problems. How do we compare the costs, the lifetime costs of different plants with different fixed costs and marginal costs? Let's do an example. The approximate cost for new generation plants for conventional coal and natural gas, this is coming from the Energy Information Administration in 2016. The fixed costs are about $0.9 million per megawatt. That's the capital cost of building a new coal or natural gas plant. plus $30 per megawatt hour in fuel and operating costs. So that's basically their marginal costs. Then wind is about 1.5 million per megawatt. That's their fixed cost. Plus $0 per megawatt hour. That's their marginal cost. The marginal costs are zero. So they're essentially their only costs are going to be their fixed costs. And then solar is a little higher at $2.4 million per megawatt in capital costs, and again, zero marginal costs. To compare costs, we use this thing called the levelized cost of energy, which is given by the formula on this slide. It's F, which is the fixed cost. That's going to be the, for example, for the conventional generation, it's going to be 0.9 million times the capacity of the unit you're building. So if you have a 100 megawatt capacity coal generating plant, then you're going to multiply 100 megawatts times 0.9 million per megawatt to get the fixed cost, plus the sum of the discounted marginal cost times the quantity produced. So this is basically the total marginal cost of producing over the lifetime of the machine. So the sum from t equals 1, that's the first year, to capital T, which is the end time period. And the denominator of this expression is the present value of the total production from the machine. So the sum of QT discounted to the present value. QT is the generation in megawatt hours. So it's the levelized cost of energy is essentially the total cost of producing energy from the generating unit over the lifetime of the unit, discounted to the present value, divided by the total number of megawatt hours that the unit produces. So it's sort of like a normalized present value cost of producing with the unit. There's this company called Lazard that produces estimates of the levelized cost of energy across different types of generation units, and they do this every year, and this is the one from 2019. That's the latest one they have. And you can see they give a range. If you want to know why they give these ranges, you can read up in their Google Lazard levelized cost of energy, and you'll find this. It's the first thing that pops up, and you can read about what these ranges indicate. But here we can see some of the highest costs are solar PV rooftop residential, so that's household solar. So this is essentially saying it doesn't make sense for you to put rooftop solar on your house. Then a couple rows down, you have solar PV at the community level. We have some of this on LeMay and Mulberry. This is basically community scale solar. And then you have a couple rows down from that, utility scale solar. So this is solar purchased by the utility and put up around the coal plants or natural gas plants or wherever it's most cost effective for them to do so. We'll skip down a couple to wind. You can see wind has a pretty low levelized cost of energy. And then we'll go into the conventional, which is the last four rows here. We have gas peaking. Gas peaking is kind of inefficient natural gas production. It's relatively expensive. Nuclear, which is pretty expensive as well. Coal, which is surprisingly expensive. And then gas combined cycle, which is actually fairly cheap. And that's the more efficient natural gas turbines. So what's interesting here is that the bottom end of wind and the bottom end of solar, utility scale solar, are below all of the conventional generation units at this point. So these are unsubsidized, meaning these are costs before subsidies. So these things are actually becoming really, really competitive, cost competitive, which is great. Here's the levelized costs over time. So this is levelized cost from Lazard from 2009 to 2020. What's interesting here is you can see back in 2009, the yellow line, this is solar PV, the yellow line back in 2009 was the highest. It had a levelized cost of energy of about $360 per megawatt hour. Now it's one of the lowest, at about $37 per megawatt hour. So these things, the cost of producing electricity with a solar has been declining substantially over time. Same with wind. You can see wind here is actually, that one has been fairly stable, but it's declined a little bit. But still, these are lower than gas combined cycle, coal, nuclear. So these are really becoming more and more cost competitive over time. They're not perfect, which we'll get into in a moment. Another caveat to this, so the previous slides don't consider the greenhouse gases from fossil fuel production. Fossil fuels produce greenhouse gases which are currently externalities. They're not priced. If these externalities were priced via taxes or cap and trade, for example, then renewables would almost certainly have lower costs than coal and natural gas. So it would push those. It wouldn't change the cost of renewables, but it would push the cost of coal and natural gas in the previous slide up. Features of renewables, number 2, limited flexibility for choosing location. So the production from wind and solar depends on the climate where they are located. You can't put solar up in Alaska in the winter because it's not sunny. You can't put a wind farm in a place that's not windy. Construction of new transmission lines is necessary to transport electricity from generators to population centers. For example, West Texas and Wyoming are great places for wind generators. There's consistent and steady wind, but they're far from major cities. So Colorado actually has a problem with this because it's really windy up in Wyoming, and Wyoming is putting a lot of wind power creating a lot of wind power, but we don't have transmission lines to meet the capacity or the demand. So there's actually kind of like a backup of wind power in Wyoming, and some of it's being sent over to different parts of the U.S. because we just can't get it to Colorado. We don't have the transmission lines to get it to us. Wind and solar generation is intermittent. This is the third kind of issue with renewables. Annual generation per megawatt of capacity is lower for wind and solar than for coal or natural gas. So think, for example, if you have a 100 megawatt capacity coal plant, you can just feed coal into that thing whenever you want, and it's going to produce 100 megawatt hours of electricity whenever you want it to. Not for solar. If you have a 100 megawatt solar field, it's only going to produce 100 megawatts when it's really sunny. Not at the nighttime, for example. And then there's a mismatch between the availability of renewable energy and peaks in electricity demand. This is what this graph on the right is showing. This comes from The Economist. This graph is what's known as the duck curve. And what this is showing is electricity demand in California net of solar production, solar supply, for different years. And California has this problem where they've been subsidizing solar generation quite heavily over time. And you can see that the different curves here are different demand curves net of solar generation for different years. 2012 was the top one, that's the light blue line. You can see that there's a nice little bump in demand right when people start getting up and going to work. And then it kind of dips down and peaks around 4 to, what would that be, 7 p.m. 4 to 7 p.m. we have a ramp up and then a peak right at 7 p.m. So demand has been increasing over time. You can see that peak at 7 p.m. jumps up quite a bit over time. But also the total demand net of solar supply is dipping down substantially, going from about, let's say at about noon in 2012, we had about 21 gigawatts demanded net of solar supply, and then in 2020 we're down to about 12 gigawatts of energy demanded net of solar supply. So you can see this dip, this sort of belly of the duck, is due to more and more solar coming online in California over the years, and supplying the demand during the sunny hours of the day, noon to, well, maybe a little less than noon all the way through about 5 p.m. And the real problem for generators now in California, conventional generators, is this steep ramp up period, kind of highlighted in gray, during the peak hours when demand is increasing. Everyone is getting home and turning on their stoves. They're getting home, doing all their chores. They're washing their laundry. They're turning on their AC. Whatever it is they're doing, that's causing a peak in demand. But this is also when the sun is going down, and so solar supply is declining rapidly. And so this causes a real problem for conventional generators that have been kind of offline during the main part of the day, and then right when the peak happens, they need to ramp up. And this puts wear and tear on their machines, and they're not really built to do this, especially coal plants. They're not really built to ramp up quickly, and so California is trying to figure out what to do with that. This would be this problem would be solved with electricity storage really easily. Again, wind and solar generation is intermittent. This intermittency provides a strong incentive for investment in storage, right? So as we just saw in the duck curve, if you had storage, you could produce during the low demand periods, like the nighttime, or periods when solar is producing quite a bit, save it up, and then dispatch it during the peak hours. This also means that more electricity capacity must be put in standby for when wind and solar generation disappears. So as you could see on the duck curve, in 2020, a lot of the demand during around noon is being supplied by solar. What happens when clouds come over and stop solar production? Then those conventional generating units need to ramp up really quickly and supply the excess demand. The environmental benefits depend on existing generation technology. So we need to think about what is the renewable replacing. We think that renewables are great as they are in terms of environmental benefits, but how great they are depends on what technology they're replacing. Investors want to produce electricity during days and hours when the wholesale price is high. So peak electricity demand is 5 to 7 p.m. That's when the wholesale prices are highest, because that's when demand is highest. And so the wind and solar companies want to produce during those times. For the environment, we want renewable generation during the hours in which the marginal generating unit has the highest emissions. So for example, when the marginal generation unit is coal, this is not necessarily during the peak hours. So this is a mismatch of when prices are high versus when emissions are high. The marginal generator is usually a natural gas generator when prices are high. So typically what's happening is these renewables are replacing natural gas instead of coal. And so we're not getting the environmental benefits that we could possibly be getting if we, for example, had battery storage. So the readings for this section coming up are the Economist article on oil majors becoming electricity producers and colon 2013. I want you to read through section 2.